welcome back to my class. I hope you all are doing well. In our last two classes on network theory, we learned about KVL and we learned about how to apply mesh analysis, which is one of the important methods to simplify an electrical circuit. Now, there is another important method which is Kirchhoff's current law or node analysis that we frequently use to simplify electrical circuits or networks or to find the desired parameter or response of the system. So we should be well aware of this law. So I will again cover about this law, how to apply this law, and we will be solving a few numericals based on this KCL or node analysis. And this is our first class on KCL.
First we have to see what is Kirchhoff's current law. Now the law says the algebraic sum of currents at any node of a circuit at every instant of time is 0. So first we have to see that what is a node. Node is a junction of two or more branches of an electrical network. So as you can see here, we have an electrical network like where we have three resistors connected this way or connected in parallel, and in that same network we have a current source. Suppose this current source is supplying a current having value I, and through these three resistors the current, and this current source, as we can see here, the direction is this way, and through these three resistors the current which are flowing, they are suppose I1, I2 and I3, and they are flowing from left to right through each of these resistors. Now again through this branch, the current having the same value of I, that current will be flowing through this branch. Now we have to see that what is the node here and how many nodes are there in this circuit. As we can see here at this point, 1, 2, 3 and 4 branches are connected. Now node is a point, as I said, that where two or more branches of that electrical network will be connected, and one end of those branches will be connected at that point or that node, and that point of those elements or those branches will be at the same potential. So this is one node, as we can see in this network. And again if we come to the other side, then here also again 4 branches are connected at this point. So this is another node of this network. So in this network we are having 2 nodes. Now as per the law, what it says is algebraic sum of currents at any node of a circuit at every instant of time is 0. And in other way we can say that at any node the algebraic sum of the currents which are entering that node will be equal to the algebraic sum of the currents which are leaving that node. So if we consider this node, what we can see here, that the current which is entering this node is only this current I, and the currents which are leaving this node, they are I1, I2, I3. So here the algebraic sum of the currents which are entering that node, that will be I only, considering this node, and the currents which are leaving that particular node, if we take the algebraic sum, then they will be equal to I1 plus I2 plus I3. Now as per this law, the algebraic sum of the currents which are entering, that will be equal to the algebraic sum of all the currents which are leaving that node. So as per this law, or as per Kirchhoff's current law, this will be our equation. I will be equal to I1 plus I2 plus I3. Now if we come to the other node, then we can see here that the currents which are entering that node, they are I1, I2 and I3. So if we take the algebraic sum of all those incoming currents with respect to this node, then it will be I1 plus I2 plus I3. And with respect to this node, what is the current which is leaving? That is the only current which is I. So it will be equal to I. So this is what the Kirchhoff's current law says. Now suppose if we take another example, say at a particular node multiple branches are connected, and those branches can have any component. So suppose if I consider that those branches are having resistive load or resistances. This way, suppose we have 5 branches, and suppose through some of the branches the currents that are entering that particular node, suppose through these two branches the current are entering that node and they are I1 and I4, and suppose through the rest of the branches the currents are leaving I2, I3 and I5. So here with respect to this node, this is a part of a particular electrical network. So with respect to this node, what are the currents which are entering that particular node? They are I1 and I4. So what we have to do is, first we have to take the algebraic sum of those incoming currents, and then we have to take the algebraic sum of all the outgoing currents, which are I2, I3 and I5, and as per the law these two algebraic sum will be equal to each other. So this is what KCL says. Now we will see when we have a parallel branches, then how a current from the current source gets divided into different parts, and how much current flow through those different parallelly connected components. Now in this simple circuit we have two resistors having resistance values R1 and R2. They are connected in parallel with each other, and with them there is a current which is again connected in parallel, and that current source having value I. Now this I, the main current source, the current will come out from that current source, or the current in that circuit will be supplied by this current source, and that current after coming at this node it will be divided into two parts, and suppose those two parts are I1 and I2. So I1 current is flowing through this resistor I1, and I2 current is flowing through this resistor R2. Now what we have to do is, what we have to find out the values of I1 and I2, and those values will be based on R1 and R2. So next we will see how I1 and I2 can be calculated. So here, if we first what we have to do is, first we have to find out the equivalent resistance of this parallel part of this circuit. So as it's simple, we already know that how to find out the equivalent resistance. So the resistance, individual resistances are, or their values are R1 and R2. So equivalent resistance of this parallel path will be nothing but R1 R2 upon R1 plus R2. Now since all these elements are connected in parallel, so as we know, in case of parallel circuit or parallelly connected component, the voltage drop is same. So if we assume that the voltage drop across this parallel connection is V, then what will be V? As per Ohm's law, we know that V is equal to IR. So main current, so V will be main current I into the equivalent resistance of that circuit. So it will be R1 multiplied by R1 R2 upon R1 plus R2. Now we have to find out the individual currents that are flowing through this resistors. So how we can find out is, I1 will be equal to, again it will obey the Ohm's law, so it will be V upon R. Since again the voltage drop across this R1 and R2 will be same, so the same that we have already calculated, so we can take that value, and this R will be nothing but R1, since we are finding out the current through R1 resistance. So it will be nothing but R2 upon R1 plus R2 multiplied by I, means the main current. Similarly, if we want to find out the current value I2 which is flowing through R2 resistance, then it can be calculated again by applying Ohm's law. So I2 will be V by R, potential difference across, or voltage difference across this resistor, which is V again, divided by the resistance value. So it will be again this V, R1 R2 upon R1 plus R2, and then the whole thing will be multiplied by 1 by R2. So R2 will cancel each other, so what will remain? finally is R1 upon R1 plus R2 multiplied by the main current. So what we can see here, when we have found out I1, the expression is R2 upon R1 plus R2 multiplied by the main current. And when we have find out I2, the expression is R1 upon R1 plus R2, again that is multiplied by the main current. So in both the current expressions, the denominator is same, which is R1 plus R2, that means summation of both the resistances, and that the same factor is multiplied by the same current, which is the main current, and I. So only difference is in the numerator, and that is when we have find out R1, that current in the expression of I1, which is the current flowing through R1 resistance, we have R2 in the numerator, and in the expression of I2, which is the current through R2 resistance, we have R1 in the numerator. So I1, only difference is the resistance value in the numerator, and that is the opposite resistance. So you have to remember that if the current is I1, so the resistance that we have to take in the numerator in the expression, that will be the opposite resistance, which is R2. And if the current is I2, then we have to consider we have to take the resistance value of the opposite resistor, that which is R1 here. Rest of the thing is same for both the currents. Now suppose if we instead of having two resistances, if we have say one or more than two resistances in this circuit, so what we have to do is, suppose we have another resistance in that parallel branch, and the resistance value of that parallel branch or that resistor is suppose R3, then how to find out the current values? So here we will have another part of the main current, which will be I3, and by applying the same concept we can find out the current value through all these parallel branches. So here what we have to do is, first we will again for all those parallelly connected components or branches, the voltage drop across every branch will be same. So what we have to do is, you have to calculate these currents in two steps. First we will find out the equivalent resistance between R2 and R3. So for that resistance is R, if we denote by R suffix 23, then it can be written as R2 multiplied by R3 upon R2 plus R3. And then what we have to do is, we have to find out the equivalent resistance between R1 and R23, which is the equivalent resistance between R2 and R3. So that resistance value, if we take as R123, then that will be R1 multiplied by R23 upon R1 plus R23. And then when we will find out the current values, first what we have to do is, first we will apply the current division rule between R1 and R23, and we will find out the current value which is flowing through R1. So individual the current which is flowing through R1, that we will get, and the another part, another current that we will find out in this case, that will be the current which is flowing through this equivalent resistance R23. Next what we will do, we will again apply current division rule between R2 and R3, and we will find out the individual currents which are flowing through R2 and R3. Now we will simplify this electrical network, and we will find out the current which is flowing through this 4 ohm resistor. Now we can simplify this electrical network by using KCL. The first thing is these three branches are connected in parallel, and second thing is the energy sources which we have in this circuit, they are current sources. So if we want to apply KCL, the first thing that we have to do is, we have to identify the number of nodes. Now in this circuit, what we can see here, at this point there are three branches which are connected. So this can be marked as a node. Suppose if we name this as A, and then here also we can see that 4 branches are connected at this node. So this can be our another node, and if we mark this as B. Then if we come to the other part, then this point and this point, they are same. And if we come at the bottom of the circuit, then at this point we can see that this current source, this resistor and this resistor, these three components or branches are connected at this node. So we can consider this as our a separate node, and we can name this as C. Now what we have to do after identifying the different nodes that this electrical circuit has, we have to assume the potential of that node. And as I said, that end of with respect to that node, every end of the connected branches, they will be at the same potential. So of node A, if we assume that the potential is VA, then this will be the potential of every end which is connected for all these branches. So VA will be the potential of one end of this current source, VA will be the potential of one end of this resistor, as well as VA will be the potential of one end of this resistor as well, which are connected at this node. Similarly, we will come at node B, and there also we will assume that the potential of that node is VB. And then we will come to the third node, and we will assume that the potential of that node is VC. Now here, when we will apply KCL, as we know that every electrical circuit should be connected to ground, so among those nodes that we have already identified, one of the nodes should be connected to ground, and that could be any node. Now generally what we do is the node which are common to the parallelly connected branches, that we connect to the ground. So here this node is the common node between all these parallelly connected branches. This resistor and this current source are connected in parallel. This resistor and this resistor, they are not actually connected in parallel because we have a resistor here also. If we consider this part of the circuit, they are actually connected in delta. But if we look at the bottom side of this circuit, then it seems that as if these three components are connected in parallel. Now when we will be assuming this node as our grounded node. So what grounded node means, it is connected to ground, so potential of that node will be 0. So whenever we will apply KCL, one of the nodes we have to connect to the ground, and directly we will be assuming the potential of that node as 0 volt. Now what we have to do is, as per the law, Kirchhoff's current law, we have to form the algebraic equations. Now if we consider this node, at node A, as we can clearly see that there are three branches which are connected. So here at node A, the current source which is connected, the direction of current flow is already given. But the other two resistors which are connected, for them the direction of current are not mentioned. So what we can do is, we have to assume the current direction, and we can either assume that the currents are flowing, currents are leaving that particular node, or we can assume that currents are entering that particular node. But whatever convention we are following, we have to maintain for in the whole circuit. So if we assume that the currents which are not mentioned for these two resistors, they are leaving that node, then as per KCL, as we know, the algebraic sum of all the incoming currents, in this case which is 5 ampere, that will be equal to the algebraic sum of all the outgoing currents. Here the outgoing currents will be current through this 4 ohm resistor and current through this 2 ohm resistor. Now how to find out the current through this 4 ohm resistor? Now we know from Ohm's law that current value is equal to the potential difference across that particular component divided by the resistance of that component. So here how to find out the potential difference? We have assumed that potential of this node is VA and potential of this node is VB. So potential difference across this 4 ohm resistor will be VA minus VB. And what is the resistance value? That is 4 ohm. So current through this 4 ohm resistor will be nothing but VA minus VB upon 4. Then we have to find out what will be the current value through this 2 ohm resistor. Now here again at node A, the voltage potential will be VA, and of the other end of that resistor we know that the potential of that node is 0 volt. So potential difference of that across that particular 2 ohm resistor, it will be VA minus 0, and then when we will find out the current value, that will be the potential difference divided by the resistance value, that is 2 ohm. So here we will be writing VA divided by 2. Now if we simplify, we will get finally it will be 20, and here it will be VA minus VB plus 2VA. So finally it will be 3VA minus VB, and that will be equal to 20, which can be marked as our first equation. Now let's see, if we assume that the currents in through these resistors, they are not leaving, they are entering that particular node. So if we consider that way, then with respect to this node, all the currents are incoming currents and there is no outgoing current. So what will happen when we will apply KCL at that node? Then we have to first consider all the incoming currents and their algebraic sum. So for this current source it is 5, and when we will find out the current through this resistor, what we have to do is we have to find out the way we did in the first step. So first we have to find out the potential difference across that resistor. And since this time we have assumed that the current is entering this node, that means through this resistor current is flowing from right to left. That means this B node is at higher potential and A node is at lower potential. That means VB is greater than VA. So when we will find out potential difference, it will be VB minus VA, and then if we divide that by resistance value, which is 4, we will find out the current value through that 4 ohm resistor. Similarly, through 2 ohm resistor, again we have considered that the current which is flowing, that is actually entering this node. So that means the potential difference across this 2 ohm resistor will be 0 minus VA, because since current is flowing upward through this 2 ohm resistor, so with respect to that current direction, this node C is at higher potential and node A is at lower potential. So potential difference will be 0 minus VA, and if we divide that by the resistance value, then it will give us the current value. So algebraic sum of all these current values with respect to that node will be equal to algebraic sum of all the incoming currents with respect to this node will be equal to algebraic sum of all the outgoing currents, and with respect to this node there is no outgoing current, so it will be simply 0. Now if we simplify this equation, again what we get is it will be 20 plus VB minus BA minus 2VA divided by 4, and that is equal to 0. So it will be minus 3VA plus VB plus 20, that will be equal to 0. That means finally it will be 3VA minus VB, and that is equal to 0. And this is the equation which is same as what we have found out in the first step. And what is the difference? Difference is, in the first step we assume that the currents which are not mentioned, the direction of current, we assume that all the currents were leaving that particular node, and in the second case we assume that all the currents whose direction were not mentioned, we assume that the currents were entering that particular node. But for both the resistors we assumed we followed the same convention, and we got the same equations finally. So whatever we are assuming, whether the direction of the current which is not mentioned in the circuit, whether we assume that as the incoming current or outgoing current, finally we will be getting the same equation, but we have to follow the same convention for the whole circuit. Now this is the equation, the first equation that we have derived from the first node. Now since in this equation we have two variables VA and VB, to solve that we need to have or find out another equation. So what we can do is, since we have another node in this circuit, so we will come to that node, and from that node we will again apply KCL and we will form another equation which will have both the variables VA and VB. Now if we simplify those two equations, we can easily find out the potential values at those nodes A and B. So let's form the equation from node B. Now at node B, as we can see here, we have four branches, two current sources whose current directions are already given, and there are two registers where the current directions are not mentioned. So what we will do, since for the first case, let's take this convention where the currents were leaving that particular node. So here also for this node, the registers for whom the direction of currents are not mentioned. So here also we will be assuming that currents are leaving that particular node. And with respect to that assumption, we have to follow, we will apply KCL and we will finally form the equation. So here the first we have to see what are the incoming currents. Now here the incoming current is only one current, that is 10, has the value 10 ampere, and then we have all branches are having the currents which are leaving that particular node. So first we will write the algebraic sum of all the incoming currents, so that is 10, and then we will take the algebraic sum of all the outgoing currents. So here we have one current source which current direction is leaving that particular node, that is 5, and then we will find out the current value through this 4 ohm resistor. Now here with respect to this node, we have assumed that the current is leaving that particular node. So we will forget about the direction what we assume, and only we will consider the direction with now for the time being what we have assumed with respect to that particular node. So here the current is leaving this node. So with respect to that direction or assumption, B will be at higher potential and A will be at lower potential. So the potential difference will be VB minus VA. And if we want to find out the current value, then it will be VB minus VA divided by the resistance value, which is 4. Then we will find out the current value through 6 ohm resistor. Again the current direction is with respect to this node, it is leaving. So with respect to that assumption, B will be at higher potential and C will be at lower potential. So potential difference will be VB minus the potential of C, which is 0. And then if we want to find out the current value, so we have to divide by the resistance value. And then we have to take the algebraic sum of all these outgoing currents. So this will be our equation that we can have after applying KCL. Now we will simplify this. So finally the equation will be 3VA plus 3VB plus 2VB, it will be 5VB. So finally the equation that we will have is 3VB plus 2VB, it will be 5VB, and here we have minus 3VA. So we can write VA first. So it will be minus 3VA plus 5VB, and then we will have 120 here, 60 here, so it will be 60, and this will be marked as our second equation. So here we have in the first equation 3VA minus VB is equal to 20, and in the second equation we have minus 3A plus 5VB which is equal to 60. So easily we can solve these two equations and we can find out the values of VA and VB. So our first equation is plus 3VA, then we had minus VB, and that was equal to 20, and in the second equation we had minus 3VA plus 5VB, and that was equal to 60. So if we simplify these two equations, if we solve, then we will be having 4VB, and that will be equal to 80. So VB will be equal to 80 by 4, that is 20 volt. So VA we can find out this way. From the first equation, it will be 20 plus VB upon 3. So it will be 20 plus VB itself is 20 divided by 3. So it will be 40 divided by 3, which will be finally 13.33 volt. Now the final requirement of this problem was to find out the current value through this 4 ohm resistor. Across this 4 ohm resistor, the two ends are A and B, and their potentials are VA and VB, and we have already found out those values. We can see that the VB has value 20 volt and VA has value 13.3 volt. So VB is at higher potential compared to VA, or B is at higher potential compared to or with respect to A. That means finally the current which will be flowing through this 4 ohm resistor, that will be from B to A, and that current value will be the potential difference across that resistor, which will be VB minus VA, because VB has greater value, then divided by the resistance value, which is 4. So it will be 20 minus 13.33 divided by 4, and finally this value will be 1.67 ampere. And this current is basically flowing from B to A. So with respect to this circuit, it is from right to left.